My name is David Richie. I'm from Brown Deer Technology. And what I'm going to discuss today is using OpenCL to design molecular dynamics simulations that target hybrid CPU-GPU architectures. So here's a sort of a roadmap of the talk. I'll start by introducing the physics that the application will address and go through that with just enough detail to transition to the software development and software design discussion. And then I will conclude by showing some performance results using a single node. So here's the motivation for this work. Molecular dynamics is an application that's been used quite a bit to demonstrate GPU acceleration for HPC applications. So there's quite a few molecular dynamics codes out there that are GPU accelerated. The approach typically has been to accelerate the most computationally intensive parts of the application. So with this kind of approach, the CPU and GPU work together. They divide up the work based on the perceptions of what each is best at. In looking at this work, this sort of raises the question, what are GPUs not good for within an application like a molecular dynamics simulation? And one of the things I've actually noticed is that over the last several years with GPU compute, the answer has sort of been changing as the question keeps being asked. Initially, there was the perception that was a very limited part of the MD code that you could actually accelerate with GPUs. So this actually led to what was sort of a software design exercise in which multi-core CPUs and many-core GPUs, the idea here is to treat them equally as processors and not using the GPU as a coprocessor. So in order to do this type of design, this is enabled by OpenCL, which allows you, of course, as we've all heard, to target both the CPU and the GPU on sort of an even footing. This particular work is also enabled by an interface that we've developed. It's a C interface to OpenCL called Standard CL. It's designed for typical Unix C programmers using sort of familiar syntax and semantics. And it makes it a lot easier to develop HPC applications quickly. So in this approach, the host platform is going to act as nothing more than a scheduler. It's essentially an operating system for your compute devices for a highly parallel platform architecture. In order to make the design exercise interesting, we chose what is sort of a very difficult molecular dynamics, a difficult molecular dynamics case as a target. The specific application we're targeting is parallel replica molecular dynamics for silicon using a Stillinger-Weber three-body potential. The three-body interaction is the key in terms of why this is actually a fairly difficult problem for GPUs. Just to sort of summarize, the objective here is to put the entire calculation onto the GPU, onto the OpenCL devices, to leave no computation on the host. So just as a way of background for those unfamiliar with molecular dynamics, perhaps, molecular dynamics is a method for simulating materials at an atomistic level. Essentially, what you do is you integrate the equations of motion for each of the atoms. You do this iteratively over small time steps, so you just sort of advance your simulation in time. At each step in the simulation, you calculate the force on each particle due to the neighboring particles for the particular interaction that you're treating. A critical characteristic of molecular dynamics simulations is the choice of this potential, this interaction between the atoms. All classical molecular dynamics potentials are approximations. None are exact, none are precise, and it's sort of an important point. They're all designed to make the physics tractable. If you were actually to calculate the physics correctly, you would have to do this quantum mechanically, and the computations are not tractable. So everything is an approximation. So a classical potential for molecular dynamics, you simply try to fit a potential and hope it works. So there's a lot of faith. You have to have a lot of faith in your potential. There are a lot of different types of potentials, and this changes the complexity of the implementation, especially in the context of GPU computing. And then there's additional complexity in terms of what type of simulation you want to run. You can run your material at constant temperature, you can run it at constant energy, depends on your objectives. And I'll just mention, this is an example of a snapshot of a molecular dynamics simulation. It's a 511 atom silicon lattice at finite temperature. This simulation was performed entirely on a Radian 5870. Porting molecular dynamics codes to GPUs, it can be easy and it can be difficult. It largely depends on the choice of potential that you're implementing. So for example, some potentials are relatively easy to do. Variations of Leonard-Jones potential, embedded atom method potential. These are two-body potentials. A lot of the early GPU work focused on Leonard-Jones potentials. They're very simple to implement. Some potentials are actually quite difficult. These would be the higher order potentials involving many-body interactions like Stillinger-Weber, which I'll discuss. Classical molecular dynamics, in a lot of ways, it's not really a floating point problem, it's a bookkeeping problem. Modern molecular dynamics codes are really driven by the bookkeeping of trying to figure out which atoms are neighboring other atoms and trying to constrain the calculation to make it order n as opposed to an order n squared problem. What I'm showing here, this is just an example of what I would consider to be an easy port to GPU with molecular dynamics. So this was another design exercise. We ported the embedded atom method LAMPS benchmark. LAMPS is a molecular dynamics code, open source, that's developed out at Sandia National Labs. We ported it to GPU and under strict restrictions on the source code modifications. So the idea was to restrict the source code modifications to the smallest possible. No change in the CPU algorithm. The full double precision CPU algorithm is run directly on the GPU without change. There's no GPU optimization. Both the pair potential and the nearest neighbor calculation were moved over onto the GPU. So this is sort of that accelerator approach. The entire effort took less than 5 days. If I were to add it up, it probably took 3 full days worth of work to port it. This was greatly enabled by this interface that we've developed. The ironic thing is, without any optimization for the GPU, just to go through the results very quickly, this benchmark runs the fastest on a Cayman board. A little bit faster than an NVIDIA Tesla. If you actually compare it to, so this was run on a 6-core high-end desktop, so with a Phenom 1090T. If you run the reference, the original LAMPS code using all 6 cores, using the MPI parallelization that already exists in the code, it's a highly scalable code, you get 1.56 seconds. So the GPU beats the CPU out of the box in this case. And interestingly, we were also able, since it was OpenCL, we were able to run this back on the CPU. The results aren't quite as favorable for the OpenCL implementation on the CPU. We used the runtime that we've developed, and also we ran it with the AMD runtime that's available right now. Not all molecular dynamics problems are so simple. So this is the physics that we're going to treat, and I'll go over this very briefly. The idea here is the application is to look at the long-time defect diffusion within a silicon lattice. So the idea is you have defects in a lattice, and every once in a while, as the temperature heats up the material and the atoms oscillate around, the atoms can jump from one location to another. These events are very infrequent, so what you have is a very difficult simulation problem. The systems you're modeling are not necessarily that big, but you have to model them over very long time scales because the events are very infrequent. However, you have to use a very short time step in order to get the thermal motion correctly. So you essentially run your simulation for very long periods of time and absolutely nothing interesting happens. But you have no choice but to do this. What I've shown on the right here, this is just an example where the red atom there essentially jumps into the vacancy, causing the vacancy defect to move in the opposite direction. And what you see is over the simulation time, this transition happens in a very short period of time. And essentially nothing much happens after that. There are methods for dealing with these long-time simulations that use parallelization a little bit differently. Normally, parallel schemes for molecular dynamics treat very large problems. You decompose spatially your very large system. For these types of problems, the system itself is typically not very big, but you want to use parallelization to address long timescales. And so one method that was developed, the parallel replica method, The idea is actually fairly simple. You just have to keep your statistics correct. So the idea is you'll run replicas of your system on multiple processors. You run them for some period of time and you watch for a transition event, for a defect to jump. When you do have a transition event, shown there with the red arrow, what you have to do is you have to run a little longer to see if it recrosses and bounces back. If it doesn't, you can accept that transition. Then you go and you replicate that state across all of your processors. You run a little bit more to dephase, and then the statistics will be correct, and then you can begin accumulating more simulation time. So this is basically the overarching framework that we want our molecular dynamics code to treat. So here are the components, components of our calculation, the things that we need to build to actually implement this onto the GPU. First is the interparticle force calculation based on this three-body potential. And this turns out to be the most difficult problem and really dominates the optimization effort and the algorithm implementation. It really drives everything. But we also need propagators. These are the components that allow you to advance your system in time over the time step correctly. So we have to use a Langevin propagator for constant temperature. We, in turn, need a good parallel random number generator in order to make sure the statistics are correct. So what we've done here is we've implemented LCG64 based on the Spring library, which is very typically used for these types of simulations. We also needed a velocity relay propagator for constant energy simulation for diagnostics. Then for transition detection, you need a steepest descent minimization propagator that allows you to quench the system. It's the stop and quench technique. You run for a while, stop, quench your system, see if it changed, if the defect moved, then you move on. The idea is to move all of these steps over to the GPU. All right, so next I want to talk about the software design for hybrid CPU-GPU architectures. So for a very long time, this has been sort of the model. This was the approach that people used for GPU computing. The idea was you would have some sort of calculation and you would identify your bottleneck, something that looked very good for the GPU, and you would go and you would port that over. So this is the accelerator model. So some particular step, you would transfer all of your data over to one or more GPUs, perform your computation, transfer the steps back. It works nicely for many cases, and it might be the right model for some cases, but it does beg the question, is this really how we should be using our GPUs? The good part of this is that you get a potential performance boost fairly easy. It's an easy way to get started. Perhaps not so easy if you've actually implemented a complicated algorithm, but it's a relatively easy way to start. Amdahl's law will catch up with you here, and the overhead can be substantial for transferring your data back and forth to the host platform and to your GPUs. So the approach taken here is to say, let's use the GPUs as first-class processors. Let's treat them as the processor that we're going to target up front for the entire calculation. So in this case, what we're going to do, we're going to put all of the computation onto the GPUs. We can also put computation onto the CPU via OpenCL by simply targeting it as another compute device. So this sets up an interesting situation where I've just noted here there's a difference between the physical count on the CPUs and the logical count. There's one physical CPU, but it actually serves two roles in this case. So there's sort of has a logical count of two. On the CPU on the left there, on the host platform, it acts as nothing but a scheduler. It initiates these calculations and these data transfers. So it sort of performs the computation by proxy. So this is the model that we're going to build the code on. So this is largely an issue for looking at, as I said, the potential calculation. The force calculation is the most difficult part of the MD implementation. How are we going to use our GPU? A GPU is a many-core processor. So when I look at this is the Cypress architecture, and I think the same could be true for Cayman. When you look at the architecture, there sure seems like there's a lot of cores. The question is, which is the actual core? You'll find different numbers stated. So on the one hand, there's 20 SIMD engines. That's a high-level component in here. Each SIMD engine has 16 physical stream cores. And then each of those has a five-core processing element, basically. So you'll hear numbers quoted 1,600 cores for the Cypress architecture. The idea here, this is a very multi-core centric view in that I'm trying to figure out basically how do I view the GPU in the context of a multi-core CPU. And the conclusion here for this work is that it's best to view the 20 SIMD engines as CPU cores, so to speak. So we view them as 20 CPU cores They have 16-way multi-threading, which is what creates a bit of the problem in the algorithm implementation. And if for the single precision parts of the computation, you can look at it as though you have a small SSE capability. And so what we're going to do here with the GPU is what we would have done on a multi-core, and that is we're going to run replicas of the system on these 20 cores on each GPU, and then we're going to do that across cards. This is the program flow that pulls all those different components together, and the figure is sort of designed to emphasize the fact that although the host is initiating all of these steps, it's really performing no computation at all for this application. So the basic algorithm, you have to update your random number generator. You have a propagator pre-force. You have to advance the system. It's sort of a half step. You calculate all of your forces and all of your particles. And I should have mentioned, periodically you check, and you may have to repack your cells with this application, and that'll get into the data structures that I've used. Then you do the post-force calculation, test for a transition. If there is a transition, you go into the replica cycle, basically, that I described. So this is the basic algorithm that we have to implement. From a software design perspective, this is sort of the layering of the software stack that we use for implementing the application. At the very highest level, it's a C++ program. And so all of the operations there, it's nice because C++ is very functional, but it's for non-critical performance types of steps. So at the highest level, we have C++. Performance critical code is then implemented on the host side. It's implemented in C using the standard CL. C interface to OpenCL. Below that, we have the OpenCL host code, and then over on the devices, you actually have the OpenCL kernel code. One interesting thing about designing an application like this is that all of the performance, all of the inner loop critical performance is pushed entirely into the kernels that are run on the devices, and it essentially pushes the performance issues largely off of the host platform. This has a practical effect in that when you're writing your code on the host side, there's sort of a freedom there because you know that everything that's performance critical inner loops has been pushed to the side, so you don't have to worry too much. You do have to get non-blocking concurrency issues working nicely, sort of OS issues working nicely, but critical inner loop performance is pushed off onto the OpenCL kernel code. I keep mentioning the standard CL interface that we use as an interface to OpenCL. I just have one slide on that just to give you an idea of what this actually is. So OpenCL provides explicit platform and device-independent control over the execution of kernels, data movement, et cetera. There's been a lot of talk of OpenCL here this week. From a developer's point of view in practice, it's actually very tedious to use. All of the functionality is necessary, all of the capability is necessary in that it's exposed the architecture very nicely and allows you to get access to everything. But as a programmer, what you find is you begin to have to control everything. So the idea here was actually very simple, and that was to look at the typical use cases for HPC and develop an interface to OpenCL following what I would call familiar Unix C syntax and semantics. And I'll give you an example of that in just a second. So this led to the development of this interface that's actually distributed as part of this Copper Threads SDK that we've developed. It's open source, GPL licensed. It's freely available. The kinds of things this adds to OpenCL as an interface, it provides default managed contexts. You don't have to set up your context anymore. There's no command queue setup, none of that. It's all taken care of for you. The complexities of actually just working with the just-in-time compilation, that's largely hidden behind a program loader that's modeled after the normal Linux program loader dlopen. And there's also support for kernel and memory. Kernel execution and memory management support is provided as well. It's important to note it introduces no restrictions on OpenCL. In other words, there's nothing using this interface that you're now prevented from doing that OpenCL would have allowed you to do. So in that sense, the interface is very transparent. It allows you to directly go down and use raw OpenCL code if you so choose. Just as an example of a simplification, if you've worked with OpenCL, you're familiar with memory buffers. You have to create these memory buffers and manage them and manage the queues to perform write and read buffer operations. With this interface, you allocate memory the way you would normally allocate it in C. There's a call called CL-malloc. It's modeled after malloc. It behaves exactly like malloc. The only difference is the memory is shareable across devices. And it's shareable through memory sync operations. There's also a fork and wait semantics that replace the NQ, ND range calls that you would typically use for OpenCL. So it keeps it much simpler. There's no event management. Back to the physics for just a moment. So this is really the heart of the computation, the algorithm that we have to implement over on the GPU. And this is just to go over why this three-body potential is difficult. So if you look at the, I've shown the functional form for the Stillinger-Weber potential. There's essentially two parts to it. There's a two-body term and a three-body term. Some potentials only have the two-body term, for example, like Leonard-Jones, and so they're fairly easy to implement. So I've shown here on the top right, this is just showing the two-body term. Basically, you calculate the force on particle 1 due to particle 2. It turns out that when you do this, the force on particle 2 due to particle 1 is simply minus that value. So what this allows for a nice computational trick in that on CPU codes, typically you calculate the force once, you update particle 1's force, you update particle 2. So you save flops by a factor of 2. The problem with GPUs is that this leads to a potential write-back collision because you have an out-of-order write that could potentially collide with the force being updated from another thread because you have a highly threaded architecture. You can get around that by simply not taking advantage of this trick. So you do twice as much work, but you can still get reasonable performance. With the three-body term, it's a little more complicated. The force on particle 1 is due to particle 2 and 3. There are contributions here, but they're not separable. There's also a reflexive force that you could, in theory, update the force on 2 and 3, and that's what's typically done in some codes. The problem here is it leads to a very bad write-back data collision problem. And if you're not careful then and you simply don't take advantage of that trick, now the cost starts to really mount where your CPU serial algorithm can very easily outperform the multi-threaded algorithm because it's doing so much more work than what you would do on the CPU. Most molecular dynamics codes are designed around neighbor lists that keep track of the neighboring atoms for every other atom, and the code is really driven by looping over those neighbors and updating the force on each atom. This is what we have to sort of revisit here. And so we implement this without nearest neighbor lists, but in fact we use sort of a very small cell scheme. So the idea is we partition our system up into cells. Atoms are associated to a cell. The cells are designed to be of a size such that we can guarantee that there is no possibility for interaction from this cell over into this neighboring cell, so that the interactions could only be within neighbor cells. So the algorithm then is implemented as a cell-cell interaction. And then for silicon, there's sort of some order to this in that you have roughly 8 atoms per cell, but not always. As the dynamics evolve, it changes quite rapidly. But we still have an order and algorithm. So the way we implemented this then, using this cell structure, so here is what I essentially consider to be my core, and it's 16-way threaded. The idea is we dedicate 8 threads to update particles within these cells shown here. Because of the cell size, we know that there can be no write-back collision into neighboring cells. The reason is, so here is a 3-body interaction. If you're updating this force here on this particle, you may have to update the force on that particle, but it's bounded by the midpoint of this cell. So another calculation will only be interacting outside that region, or updating particles outside that region. This is the basic way we are able to use the highly multi-threaded architecture, but avoid that data write-back collision. And so the systems we'll run are fairly small. 4,096 particles is a fairly large system for looking at a very small defect, but we'll run many, many replicas. So we can run 160 replicas on a single GPU. And I'll get right to the performance results. Before I present the performance results, the benchmarks, I just want to go over what platform we're using here as a reference. So this was all run on a very high-end desktop with a 6-core Phenom 1090T. Of a fairly good motherboard, very fast memory. Then we use 4 different AMD graphics cards, the 6970, FirePro 8800, and the 5870 and the 5970. So sort of the whole mixture of cards that might be out there right now. On the software side, we're running CentOS 5.4. The code was compiled with GCC 4.1. We use the current AMD OpenCL implementation, and we also use this standard CL implementation. As a reference code, we use the LAMPS code, a recent snapshot of LAMPS, to provide a reference implementation that has the same methodology application implemented within it. And here's the performance results here. So just going from the bottom up, so this is the reference code. We're running this on using LAMPS. We're using all 6 cores. It's a highly scalable code, runs across multiple cores very well. You essentially get linear scaling when you try this. So the LAMPS code itself, you get, what I'm plotting here, by the way, this is the raw accumulated simulation time that you could expect in picoseconds from running your simulation. So remember, the issue here is we needed to accumulate large amounts of simulation time for these long-time simulations. What I'm showing here is the amount of time accumulated per 1 hour of wall clock time. So it's a very real-world metric. It's what a user might want to really know. You get you have a little less than 1 nanosecond of simulation time that you can accumulate on a Phenom. Interesting that if we just run our OpenCL implementation directly on the CPU, you actually get just a little over 1 nanosecond. So this algorithm, the way it's implemented within OpenCL, is more efficient than this production MD code. It's not to say that this production MD code is the fastest implementation of this methodology, but it's a very widely used production MD code. So the OpenCL implementation turns out to be a little bit faster. When we run the implementation on the Cayman board, we get a good amount of improvement. As you can see, for some reason, Cayman doesn't do as well as Cypress here. I'm not quite sure why that is. It's something that we're looking at. It has to do, we rely heavily on the use of local memory in this algorithm. So there may be some issues there. But when we move to the FirePro, we get a good speed up over the CPU. And if you consider the reference benchmark, we get basically 2x over that. If you run on a dual GPU 5970, you essentially get your full use of the GPU, so to speak. It's a nicely scalable algorithm. But most importantly, what we want to look at here is what is the combined performance of the platform. So if I have my desktop and I put a couple gamer boards in them, what can I expect to get in terms of the return? You get more than a 5x return in terms of accumulated simulation time by using your gamer boards here in this case. So this is a good example, and this is to emphasize this is one common code base. This is just one implementation that you can then run across your entire platform. So just to summarize, OpenCL enables device-independent CPU, GPU simulation codes. By using this approach, you get sort of a scalable platform approach as opposed to using GPUs as sort of a targeted accelerator. So the nice thing here is you can write your code once and you can run on any device, cross-vendor. In this non-trivial example that we've showed, all of the computation can be moved over onto the OpenCL device. So the full application is moved over there. CPUs, GPUs being treated as a peer. The ability to implement this was greatly helped by the standard CL interface. It simplifies HPC code development quite a bit. Just to summarize the benchmarks, the OpenCL code outperforms the reference code on the CPU. The OpenCL code on the GPU outperforms the CPU. And the combined platform provides a substantial speed up of 5x over the CPU.